All right. Well, happy Monday. Happy week 8 Monday. It's kind of crazy that it's already week 8, but here we are, and we have stuff to talk about. So, on Friday, we left off and we covered a few more root finding methods. We said this is how you find where the function is equal to 0. And what we then said was that we can turn any of these root finding methods into an optimization method. Okay? And the plan is this. We take the derivative of a function and then we solve for where the derivative equals 0. We use the root finding method to help us find where the derivative is equal to 0. That's what we said. All right? And that makes sense. That lines up with what we've learned in calculus, that to find where a local min or local max is, or maybe a saddle point, we find out where the derivative of a function is equal to 0. That's going to give us our critical points. And so we can take all of the root finding methods that we learned earlier, all of these root finding methods, and all we have to do is we apply the root finding method to a derivative, and that will give us a way to find a local min or local max. And so I just gave a quick example for the Newton-Raphson method. If we wanted to turn it into optimization, all we have to do is we'd say, all right, we have some function g of x, okay? And we're going to let f of x equal g prime of x. And if we do that, we can find the roots of f of x, which uses this algorithm, xn minus f of xn over f prime of xn, and that will give us our next iteration value, and we just use that, okay? So if we said, well, f of x is equal to g prime of x, then we could just rewrite the whole thing and say we're going to do this, where we're going to subtract off g prime divided by g double prime, okay? And this should work towards finding a local min or local max or a saddle point of g. Okay. Now, one objection or one question that you might have is, well, what if I don't know how to take the derivative of a function? Okay, like this is great, finding and optimizing a function. All we have to do is take the root finding method and apply it to a derivative. Okay, but then what do we do if we can't figure out the derivative? Okay, because taking a derivative often involves calculus or something. What if we're struggling with that? Okay, what can we do? Well, we have some numeric methods for approximating a derivative. Okay, so let me just kind of write this down. So earlier we said, oops, change this to that. So okay, so we can find a local min, local max by using a root finding method on the derivative of a function. Okay. So just basically find where g prime of x is equal to 0. But what if we have trouble finding a derivative? Okay. So what we can do is we've got basically numeric approximation, right? All of these numeric methods are going to give us approximations. So all of our root finding methods, they just zero in on approximations anyway. Okay, what is the definition of a derivative? Come on, you guys. All right. definition of a derivative. Okay, all right, well, I'll give you a hint. It's a limit, okay? It's the limit of what? Limit as what goes to what? Okay, yeah, all right, so we're gonna say limit as, I'm gonna call this delta. Limit as delta goes to 0 of, we're gonna say, we've got, I guess we're using g. Okay, so g prime of x, so this is just a single prime. Okay, so g prime of x is equal to the limit of g of what? X plus delta minus g of x divided by delta as delta goes to 0. So this is the idea of our derivative, okay? And what we can do then is, you know, we don't have to learn all of these differential rules, right? Like, there's some, like, you learn simple ones in your differential calculus class, right? Like, the derivative of x cubed is going to be 3x squared and stuff like that. But we can't teach the computer that. All we can ask is the computer to just calculate numbers for us. And so we're going to just ask it to calculate these numbers for us, okay? And one thing that we're going to do, so let's say we've got a function like this, and let's say this is our location x, okay? What we're going to do is we're going to take, we're going to add delta. So this spot is going to be x plus delta, and we will find, I guess, f of x plus delta. That's fine. All right, and I'm also going to go the other way and subtract off delta. So I'm going to have x minus delta, and this will be f of x minus delta. All right, and so my derivative approximation is going to be f of x plus delta minus f of x minus delta divided by what? 2 delta, right? And that will give me an approximation of the derivative at x. And so that's what we'll do. This is how we will approximate the derivative of a function, even though the computer doesn't know calculus and doesn't know derivative rules. It doesn't know derivative of sine is cosine of x. It doesn't know that the derivative of e of x is e of x, or things like that. It doesn't know chain rule. It doesn't understand any of this stuff. All it can do is just plug in numbers and spit numbers out. But that's good enough for us, okay? So I've written up just like a very simple derivative function. Okay, so here, so the function I'm going to take the derivative of is 1/4 x to the 4th minus 1/2 x squared. So I'm going to let g of x be 1/4 x to the 4th minus 1/2 x squared, okay? And I have the 1/4 and the 1/2 just so that when I take the derivative, it's going to be easy to work with. Okay, so g prime of x will be what? X cubed minus x, okay? Just so things are easy for us. But anyway, so I've got g is this. Hang on, sorry, let me delete everything in my environment first. Okay, so we'll start off with a sequence going from -1.8 to 1.8. We'll ask for g and calculate g applied to x, and we'll plot this. Okay, so this is what the function looks like. Let me figure margin's too large. We love that warning, right? This is much easier, actually. Okay, so this is our function here. Okay, and just so we can see this, I'm going to create a function called derivative, And the derivative is just going to ask for a function, okay? And it's going to ask for the x value. And it asks for a delta, but we're going to give it a default value of like 1 times 10 to the negative 5. You can choose something smaller, but obviously not too small where you're going to run into machine error problems, okay? And then we're going to have x on the left is x minus delta, x on the right is x plus delta. We're going to calculate the function x to the right minus the function of x to the left. And we're going to take that and divide by 2 delta. And we're going to return that value of d. Is that okay? Let me just draw the x-axis here also. So I've got AB line 0, 0. Okay. Is that okay? And so I can just kind of say, well, what is the derivative of g of x, g, if I go to 1.5? Okay. And so it tells me it's 1.875000000. If I say my options digits equals like 8, then I get 1.875. The actual derivative is x cubed minus x. So I could just try that. 1.5 raised to the 3rd power minus 1.5. And indeed I get 1.875. Okay? So we're getting pretty good approximations. Obviously if I keep more digits, the derivative is that where the actual derivative, at least up to numeric floating point precision, gives me 1.875. So, you know, we're off by a tiny bit, but up to 8 digits, we're accurate. So I'm not too worried, okay? So that's the derivative right there, okay? Okay, and so here I'm going to create a new function called numeric g prime. Okay, so it's basically I want g prime, and all I'm doing is I'm just calling the derivative function on g, and we're going to plug in whatever x value we plug into numeric g prime. Okay, so up here we have the derivative function, and then now I'm creating a new function called numeric g prime, and I'm going to apply numeric g prime to my vector x, and we're going to get a bunch of g prime of x values. Okay, so I'm going to go ahead and draw that. And as expected, the derivative of a power, 4th order polynomial is a 3rd order polynomial. Okay, we have a 4th order polynomial, and its derivative is a cubic function. And so here, I just wanted to kind of compare what is the how does my numeric approximation, which is used only by doing x minus delta and x plus delta and finding the function values of those two things, how does that compare to the actual derivative? So if I use the actual derivative of using x to the 3rd power plus x, minus x, and I calculate the actual derivative on all of these things, I can graph that. I'm going to graph that in green on top of this blue line. I'm going to do a dotted green line on top of the blue line, and we can just see, how well does it compare. And when we look at it, just visually, they line up like exactly on top of each other. Okay, so that's a good sign. And we can actually use a function. There's a function called all equal, right? So if I did options digits equals 17, and I ask for, what is kind of in my numeric g prime vector, what's the first value? I have negative 4.032000, and we have some kind of leftover values over here. And if we ask what is the actual g prime at that thing, we have something that's a little bit different, okay? I think the actual value is negative 4.032, but because of floating point precision, it's off by a little bit, okay? All equal, so, if I did this, is this equal to this? It's going to return back false, right? But all equal does, what all equals asks is, it just says, are these two values nearly equal? Okay, are these two objects nearly equal? And it comes with a default tolerance level. So you just kind of give two values, and there's a default tolerance level. The default tolerance is around 1.5 times 10 to the negative 8. Okay, and this allows for kind of basically rounding issues because of floating point arithmetic, or if we're doing like numeric derivative approximates, it just kind of says, you know, are these two things nearly equal? So this is not good for proving anything mathematical, okay? Which is not what we're trying to do. We're just trying to get approximations with the computer, right? That's kind of the whole point of using the computer. And so we're going to use all equal, and if we ask, is the numeric gradient or the numeric derivative equal to the actual derivative in terms of being nearly equal using all equal, that returns back true. Okay, so you know 4.03200000209, you know, whatever. We've got some difference here, but that's within the tolerance where we're around 10 to the negative 8. Okay, and if it's bigger than that difference, then all equal will come back and say, there's a little bit of a difference here. Okay, I think you guys saw all equal earlier when you were doing like is Arizona Diamondbacks equal to Arizona non-breaking space Diamondbacks, and things like that. So you can just give it kind of two vectors, and it will just kind of check to make sure that everything is the same or not. But it's very useful for comparing two numeric values to just see if they're within some kind of tolerance level. And you can manually specify the tolerance if you need something even more stringent, or if you want to relax those tolerance requirements. Okay, so this is very useful because again, we're not dealing with real numbers, we're dealing with computer numbers. Okay, and I'll post my code here, but this technique of estimating the derivative numerically is very useful in like machine learning contexts, because we often need to calculate the derivative or gradient of these complex functions, and it's often quite difficult. And so you'll have you'll do calculus and get something because it's usually faster and better that way, but then you'll compare it to a numeric approximation to kind of just see if the answer you found was correct. So anyway, I'll go ahead and I'll copy this to kind of just show that these two things are so here we have, in green is the actual derivative, which is x cubed minus x, and then blue is the numeric approximation. Okay. And this, so again, we have this function called numeric g prime, which just takes the derivative function and applies it to g. We can do this a second time to get g double prime. Okay, so I'm going to just take the derivative function and apply it to numeric g prime, and this will give me basically numeric g double prime. Okay, so I'm just iteratively repeating this. So taking the derivative of the derivative, again, this is still just a numeric approximation. We can say, all right, what's the second derivative, right? So this is approximating the second derivative. Apply the derivative function to numeric g prime, and we're going to just ask, okay, calculate the second derivative on all of these things, and then let's go ahead and graph that. Okay, and as we might expect, the derivative of a cubic function, third order polynomial, is going to be a quadratic or second order polynomial. Okay, which is what we have now. Because we have such simple polynomials, okay, x cubed minus x, the actual derivative is very easy for us to find. That's going to be 3 times x squared minus 1, okay? And so I can just kind of compare what is the actual derivative, actual second derivative, okay? So that's going to be 3x squared minus 1. We'll calculate the actual derivative there across all of our things. And then I'm going to just graph it in a green dotted line over the red line, okay? And again, when we do this, we get, we can see that they line up very, very, very closely, okay? Pretty much, at least visually, as far as I can tell, they're identical. Okay, and then so we can ask the computer, is everything all equal, okay? And what the computer returns back is that they are not all equal, but the relative difference is 7.3 times 10 to the negative 8, okay? So the tolerance for it to come back and say that they are all equal is 1.5 times 10 to the negative 8, and we're a little bit bigger than that, 7.3 times 10 to the negative 8. But we're still on the order of 10 to the negative 8, okay? Which is like, what is that, 1 penny versus $1 million, okay? So we're probably okay, all right? So I think the current tolerance is 1.5 times 10 to the negative 8, so if it's less than a 1.5 cent difference in $1 million, it says it's the same. Now we're about 7 cents out of $1 million we're off, and so it says, uh-oh, it's not exactly the same, but probably for our purposes, these are close enough, okay? And again, we're just using these derivatives to get, to help us find roots and minimums and things like that. So, so anyway, this is, I just wanted to show that it does work in terms of finding derivatives of functions. Here's just another example. I'll graph 0 to 3 pi of sine of y, and if I plot sine of y, it looks like this. Okay, maybe I'll add the x-axis. So that's the sine function from 0 to 3 pi. Okay, and then and just using the derivative, numeric derivative thing, we can add the derivative of that. And that looks a lot like the cosine function, okay? And you know, the computer doesn't know that the derivative of sine of x is cosine of x or anything like that. It's just doing plus delta minus delta, calculating those values, okay? And then, and if I plot the cosine of x in green on top of it, you know, we see that it lines up exactly, okay? So that's pretty good, right? Okay. Are there questions on any of this stuff? Numeric approximation. And so we see our numeric approximations are very good. Very closely to the actual derivative. I guess I'll just for completeness, we'll throw in these additional plots. So this is the second derivative. Both the approximation and actual. non-polynomial functions as well. Okay. If you have a function where the derivative does not exist, such as there's a discontinuity or something like that, this is probably not going to detect it. You'll just get some kind of crazy huge number or something, most likely. So if it's like, I don't know, something. Okay. All right, let's talk about, so all of these derivative methods for optimization, okay, so these were all, the whole reason why I showed you this numeric derivative stuff was because we said we can optimize a function by using one of the root finding methods from before and applying it to the derivative of a function, okay? And if we had trouble finding the derivative of a function, we can approximate it this way. Just like the root finding methods sometimes break if things go wrong, like the Newton-Raphson method will fail to find a root if you end up in a spot where the derivative is equal to 0 or something like that, or some of these other methods, they might break. We have a optimization method that does not depend on derivatives and instead depends on using the golden ratio, and this is called the golden section search for optimization. It's no derivatives required, okay? Golden section search for optimization. All right, and what it does is it uses the golden ratio to kind of optimize a function to help us find a local minimum. Okay, so we're going to find a local min. All right. First of all, let's talk about what is the golden ratio. Golden ratio is what?
618.
Okay, yeah, 0.618, very good, approximately. But that's impressive that you know that. But conceptually, what is it? It is, imagine we have, it's supposed to be a square. All right, so I'm going to draw a rectangle. I don't know how to draw this rectangle. Okay, so here is a rectangle. And the idea here is that if this side of the square is 1 and this side of the square is 1, and we add, this side of the rectangle is 1 plus x, then what happens is that the ratio between the short end and the long end of this rectangle is exactly equal to the ratio between the short end and the long end of this rectangle. Okay? So that what we would say is that 1 divided by 1 plus x, okay, so the ratio of the short to the long, so if I do short over long, so 1 over 1 plus x is going to be equal to the short edge, which is x, over the long edge, which is 1 in this picture, right? So this has a length of x and this has a length of 1, okay? And so, now you have this quadratic thing to solve, okay, and you can use the quadratic equation and all of that, And what we find is that x is approximately equal to 0.618. And what we find is that 1 divided by 1.618 is equal to 0.618 over 1, okay? Or just 0.618. So when you do 1 divided by 1.618, you get 0.618. If you did 1 divided by 0.618, you get 1.618, okay? Which is pretty neat, okay? So so anyway, this is the golden ratio, and we are going to use this, okay? So this becomes what? 1 is equal to x plus x squared, and then solve for x. Okay, so what I'm going to do is we're going to take a look at this function, the original. Let me just clear all of this out. Okay, we're going to take a look at this function, but I'm going to just zoom in on the right-hand side. Okay, I'm going to just zoom in on the right-hand side. So we're going to just have this kind of dip down and go up, and we're going to search for a local minimum on the right-hand side of the graph. Okay, so the function is 0.25 or 1/4 x to the 4th minus 1/2 x squared, and so I'll draw this, and I'm going to just go from 0 to 1.5, and I'll plot this. Okay, so this is, we want to optimize this function here. So I'm going to go ahead and I'm going to copy this. So we're going to have f of x is equal to 1/4 x to the 4th minus 1/2 x squared, and our plot looks like this. Okay, and we want to find a local minimum. Okay, so over here I've got my left bound, or I'll call this my lower bound. My lower is x equal to 0, and my upper is x equal to 1.5. Oh, that's not. You write 1.5. Okay, so that's my lower bound. Here's my upper bound. X equals 1.5. And all we know is that we know a local minimum exists between 0 and 1.5. Okay. We know. We'll say. We'll just start off, and we'll just for simplicity, we'll say we know one local minimum exists between 0, or we'll say the lower and upper bounds. Okay, so we know one local minimum exists between the lower and the upper bounds. And what we're going to do is we will find x1 and x2, okay? We're going to find kind of these two midpoints, not actual midpoints, but we're going to find two test points inside that is going to be the golden, 0.618 out of the way from 0 to 1.5, okay? So I'm going to find the golden ratio. The golden ratio is around 0.618. It's just a little bit different than that. And we can see that 1 divided by the golden ratio is that, and 1 divided by 1 plus the golden ratio is equal to the golden ratio itself as well. Okay, so these are some of the nice properties here. And so I'm going to do the golden ratio times the upper minus the lower bound, so 1.5 minus 0. And I'm going to add that to the lower bound, and I'm going to add that to the upper bound. And I'm going to draw kind of these lines here. go ahead and draw that. Okay, and so what this line represents, from here to here, this is 1.5 times 5, 5 being the golden ratio. And then over here, from here to here, this distance is 1.5 times the golden ratio as well. Okay, so this is about 61, 62% of the way from 0 to 1.5, and on the other way, it's 61, 62% of the way from 1.5 down to 0. Okay, and what we do is we say, all right, let's evaluate what is the value at this location and what is the value at this location. All right. So we go ahead and we do that. And we say, and this is easy, so I'm going to go ahead and I'm going to plot those two spots right there. And we ask, which one is bigger? This one or this one? Okay, and it's very easy for us to see. Okay, there's a video that I'm going to have you guys watch as part of your homework. Okay, and it calls this one x2 and it calls this one x1. Okay, so don't be upset. So we've got our lower bound, the lower, and the upper, okay? And we have x2 and we have x1. Okay, and so we've evaluated the function at x2, we've evaluated the function at x1. We haven't evaluated it anywhere else, okay? We don't even know the value of the function at the lower bound or the value of the function at the upper bound. However, we do know that there is one local minimum between the lower and the upper bound. Okay, we know that there's one local minimum between the lower and the upper bound. And so, because x1 is lower than x2, we know that the local minimum must be between x2 and the upper bound. Okay, because if there's one local minimum, and it's on the other side of x2, if it's on the left-hand side of x2, then x1 cannot be lower than x2 because the fact that there's just one local minimum means that the fact that x1 is lower than x2 means that there can't be another value on the other side of x2 that's even lower than x1. Okay? The fact that there's one local minimum within this range, the fact that x1 is lower than x2, it eliminates the possibility that there's another value to the left of x2 that's lower than x1, or lower than f of x1. Okay? So we can eliminate this side of the picture. Okay? We know there's no local minimum here. Okay, so again, we know there's one local min between lower and upper bound. Okay, and the fact that f of x1 is less than f of x2 means there cannot be another value on the other side of x2 that has a lower value. Okay? So what we will do now is that for the next iteration, we are going to make this our new lower bound, and this will remain as our upper bound. Okay, and so now we have a smaller zone, and we will repeat the process, and we will do golden section search on this section, and we're going to say, okay, I've got a lower and an upper bound, and I know that there's one local minimum between my lower and upper bound, and we're going to follow the same process. Okay, so now we have a smaller window to search. Smaller window to search, and we repeat the process. Okay, but here's the amazing thing, is that because we've used this golden ratio with the property that this golden ratio has this 1 divided by 0.618 is 1 plus 0.618 and whatever, is that this location, x1, that we have here, becomes our new x2, and this distance from the upper to x2 is going to be exactly 1.5. Not 1.5, is going to be phi, the golden ratio, times the distance from the upper minus the lower times phi. So whatever distance we have from the lower bound, the new lower bound and the new upper bound, if we multiply that distance by phi, the golden ratio, that will take us exactly to this location that we've already computed before. Okay, and that speeds up our algorithm, because if our function, if it's very expensive to calculate the value of the function at a certain location, being able to reuse values that I've already computed is very handy, right? If you had to like punch a bunch of numbers in, like let's say you had like this polynomial equation of like 100 values or something, and you had to punch all of these into your calculator, it's going to be frustrating with every iteration if you have to do this twice, okay? But if you did it twice for the first iteration, and then for the next iteration, you can reuse one of those values and just do it once for the next iteration and just continue that every single time, then your algorithm is a lot faster, okay? So now we have a smaller window to search, we repeat the process, and we can reuse one of our test points for the next iteration. So let's go ahead and just kind of show this. So I'm going to go from around 0.6 to 1.5. So all I'm going to do is I'm going to say this is x2. This is going to become my new lower bound. And I'll go ahead and just redraw this part of the graph, okay? So we're zooming in. We're redrawing that part of the graph. And because of the golden ratio, I can just reuse x1 and the old value of f, okay? And I don't have to do any new calculations. And even though I didn't do any new calculations, we can see that visually, we see that if you focus just on this green line, as far as where it is on the scale, it doesn't move, right? It's about 62% of the way or 38% of the way from the left bound to the right bound, and we can just see it doesn't move from iteration to iteration. Okay, so I can, so it remains. We're going to calculate the new other spot over here, and we're going to ask the same thing. So I know there's a local min between this bound and this boundary, And because this one over here is smaller than this one over here, we know that there can't be another value on this side that's smaller, because we know that there's just one local minimum between the two boundaries over here. And so we'll go ahead and just eliminate the side on the right. Okay. So on our second iteration, we're zoomed in over here. Okay. And again, we can just eliminate all right, so we have no, we know that the local min is not going to be over here because, so if this is x1 and this is x2, f of x1 is greater than f of x2. Local min cannot be greater than x1, okay? So we eliminate that, and then we repeat the process, okay? So this time we have that, so the x1 becomes the new upper bound. So this will become our new upper. This will remain as our lower. And then this will become our new x1. So we do that. We can zoom in over there, and we'll draw that. And we calculate this, and we continue the algorithm. Okay. So this was just very manual, just redrawing graphs every single time, which of course in real life we would not do because drawing graphs is computationally expensive. But I don't know. Am I able to line this up appropriately? Okay. So this is kind of what happens here. And we're just applying, we iterate this process of golden section search over and over and over again, shrinking our windows by around 38% each time until we get to a window that's very small and we're satisfied in saying, okay, the local min must be, just kind of halfway between these two boundary points where, our window has shrunk down to. I've provided the code for golden section search, and you guys use it in the last problem of the homework. And there is a link in the there's a link to a video in your homework. Please be sure to watch that. It's I think it's a very good video, and I tried to kind of follow the same notation of that video for here. So please be sure you watch that. Okay, we'll end there. We'll see you guys on Wednesday.